So let's start looking at SRAMs. So what does SRAM stand for? Static Random Access Memory. And we have drawn the circuit from SRAM last time for the read operation, but now let's look into the write operation. It's memory, sometimes you're going to read data from it, and also you need to write data into the memory, right? So the memory cell looks like it's a 6 transistor. So SRAMs, keep in mind, it's a 6 transistor. We don't have homework assignments regarding memory circuit design, but I'm going to put some of the really simple circuit description problems or questions in the final exam. I'm not going to let you know what are they on Monday in the final review. Is that fair? The 6 transistor. The bottom line is you need to understand what's going on within the SRAM and DRAM memory cells, right? How it works. All the memory circuit design in Dr. Baker's class is normally just for his business and his patents or research, not for education. But after he has covered some of the memory circuit design for a couple of classes, including his digital class in one or two semesters, a couple of students got employed in Micron, so that's why he was willing to cover more, and students can get a job in Micron. And so some of the groups in Micron are trying to recruit more of his students because there are not too many professors are covering memory circuit design in the US. And whenever they are covering all the circuit design, it's just show the slides. And since the professors have not done any memory circuit design and they're teaching it, so that's why the students literally won't be able to know how to design the circuits, either simulation or layout. And that's a work line, that's a bit line. That's a row selector, and you can connect the decoder to it, so you can select this line. And the first step for the read operation is what? You remember it? So keep in mind, I may have a question for you on the final exam to let you describe the operation procedure for the SRAM or DRAM. So what's the first step? Yeah, pre-charge the bit lines, both the bit line and the bit bar line. Pre-charge. The bit bar line to what? VDD. So these two lines should be pre-charged to VDD. So here's a question: how? Doing this. That's another signal to phi 2. And whenever this is low, it's going to load or source charges from VDD. So the charge will be dumped to these lines. So this will be charged to VDD. And then what? After you charge these two lines to VDD, and then do what? Float it or float them. So I'm going to charge it up to VDD, and then shut these two PMOSes off, so you can float these two lines. What's the next step? So you can give some examples. So if this is 1, this is 0, why it has to be 1, 0? Keep in mind, that can be a question on the final exam as well. Why it has to be 1, 0? Positive feedback, because that's a latch. So it's either doing this or this. All right. So for example, 1 was stored here and 0 was stored here. And these two has been pre-charged to VDD, right? And being floated. So next step, and this is Q, that's Q bar. So if Q is 1, Q bar is 0, then what? Fire. So actually you want to fire the word line. Fire the word line means they just turn it on. It's another jargon in IC. You know, we just say fire, just fire it. So fire it, so you can turn it on, then what? So you can read from this bit line. So that's data line. Actually, you have so many words, but this is the only data line. This is not the data line. This is just being used as one wire in a positive feedback for the latch, right? So this is not the data. The bit bar is not the data. This is the data. So whenever this is 1 and this has been pre-charged to VDD, so when you fire the word line, right? So these two channels will be opened up. Then what's happening at that moment? So these two MOSes will be on when you fire the word line. Yeah, so these two, they have the same potential exactly, because VDD, VDD. Same potential, so no voltage drop. It stays at 1. So you can read. I know they previously stored at VDD, but now when you are reading this line, it is still VDD, it's not changing. So you can read about 1 here. If Q is 1, Q bar is 0, then it's not responding. Then read the bit line. And what's the data here? Which will be VDD, right? And what about here? It used to have charges here, and what's going to happen? Because the floating VDD is not super strong, and whenever this channel is open, and this is really strong ground, it's a really strong 0, so this NMOS is able to discharge all the charges here to the ground. So it's going to be discharged to the ground. So it used to be VDD, but now it's going to be 0, and the circuit becomes stable. So that's when you are reading a 1 from here. What if Q is 0, Q bar is 1? What's going to happen? Because it's super symmetric, it's equivalent on two sides, right? And we are still reading this bit, this line, because that's the data to be read, always. Fire the word line, the channels will be on, and the bit line will be discharged. to ground. So you can read a 0 from here. So the reason we need this latch is because it's providing a positive feedback. It's always storing all these 0 or 1s on one side. It's very stable. So if this is discharged, if this line is a floating VDD, it's not strong because I only have some floating charges. And this is really strong ground. You can discharge all the charges to the ground, so this becomes 0, so you can read a 0 afterwards, right? So what about here? Same concept. This is 1, this is 1. Even though this is a weak VDD, but however, the potential is the same, so nothing is being discharged or charged. No potential drop. It's going to stay at 1. If this guy stays at 1, it's going to even strengthen that 0 because it's the positive feedback. So whenever this guy is discharging the VDD, it's not going to change anything. The reason is this guy is super strong. It's holding all the voltages here at 1. If this is 1, it's a positive feedback. If this is 1, it must be 0. No doubt. So that's how you read data from the SRAM. And the reason it's called static RAM, I'll also ask you what's the full name of SRAM. Static random access memory. It is static. The reason it is static is because this is a super stable latch. It's going to hold the values steady at 1 or 0, right? It's just being compared to the counterpart, which is the DRAM, is not really stable. I'm going to let you know why. Any questions with the reading operation of the SRAM? No? Oh, this is a memory cell. That's a 6-transistor memory cell. These are some peripheral circuits trying to pull it up, pull it down. There are many other transistors as well. It's just not in the cell. So that's a memory cell. You can have control bits, you can have decoders, and just everywhere. It's definitely not only 6 transistors. It can be millions. Right? The capacitors are everywhere. Even for the metal lines, they have capacitors. Because all the IC layers, they have insulation layers in between, and you have metal layers as well. So metal dielectric, you get a capacitor. Yeah, it's pretty small, but compared to the tiny transistors here, it's actually comparable. You cannot ignore all the capacitors, and this also happens in the DRAM. So all the capacitors we've been using the DRAM is only like 20 femtofarads, for example, and the metal wires running through all the circuits can be somewhere around 200 femtofarads. So who is actually storing the data, right? So that can be a problem. So we are going to talk about it really quickly. And for the DRAM, you can buy a DRAM card from the market, right? It's just the cost right now is super low. Only like $60, you can buy a 64 gigabytes card or something. The reason for that is they can integrate more DRAM cells into a smaller size with a lower cost. And so they want to integrate as many memory cells as possible for the DRAM. So they want to use smaller capacitors. And when the capacitors are smaller, the impact from the metal lines will be bigger. So that's the kind of trade-off of the circuit design. So that's read operation. And you can imagine that there can be many other cells just following. You can have one 6-transistor cell, you can have another one here. It's just being fired by a different word line. So this word line, we just call it word line 0. You can have another line to turn on the next cell. You can have many of these ones being repeated. in one direction. So next, the write operation. It's still the same circuit, but we just need some NMOS transistors at the bottom to write it. And here is the write command. Write Q, write to Q. And here's the enable. I just call it data. So what is the first step to write? For example, we want to write a 1 to here. So previously it was 0. And I want to write a 1 to here. Write 1 to Q. First step, still pre-charge the bit lines. Here's bit. Here's bit bar. And it becomes VDD, for example. So if I want to write a 1 to Q, so what kind of voltage level should I give to this line? I'm trying to write a 1 to Q. Let's see. If I have a 0 here, it's being inverted, got a 1 here. And definitely when you're writing, you need to give a command, which is 1. So both of these two NMOSes will be on. And it's open. So what's going to happen? Definitely the floating VDD is not able to handle that drawing, current drawing, right? So it's like a black hole. It's going to draw all the charges, it's going to drag it to the ground. So what about here? If this is being pulled down to the ground, and you are thinking, hey, this one used to be 1 and it's really stable positive feedback, and this one is being pulled up by this PMOS, right? So this PMOS is trying to pull it up to VDD, but these two NMOSes are trying to pull it down to the ground. They're competing. So what's going to happen? Why? It's like when you're hanging out with your girlfriend, right? She want to go to somewhere else, you want to just stay in Durango for camping, for the holiday. So who is stronger? So just want to make the NMOS stronger. How to make it stronger? Let's make it wider. Just make it super wide, like this. So everything will be pulled down to the ground. So PMOS cannot compete with NMOSes. So if this is being pulled down to the ground, then what? The latch will pull this to 1, up to 1, because of positive feedback. And then read. No, and then done. I just want to write a 1 to here, right? And now it's ready. Have this one written into this Q line. So pre-charge the bit and bit bar to VDD, and second, data, I think it's called data selection or something. Data selection, give data selection that line to 0 to it, and for write Q, definitely enable it, and done. So 1 will be written to here. That's write a 1 to Q. So now, for example, 1 has been stored in here and 0 has been stored in here. And now I want to write a 0 to Q. What's the first step? Still, pre-charge, bit, and now let's see. Definitely, it used to be 0. Now data S should be 1. Definitely want to enable it. So if this is 1, this is 0, so nothing is going to happen here, because this almost is shut off. It's in series. So this will be on. This will be on. So the previously stored VDD will be discharged. It used to be 1. It's being pulled up by this PMOS. And now you have NMOS trying to pull it down to the ground. Again, it's competing. So how? Just make this NMOS stronger. Just make it wider. So if this is being put down to the ground, and because of positive feedback, this will be put up to 1. And now a 0 has been written into Q, right? We are done with the writing operation. Any questions? So now, let's look at the layout of the 6 transistor SRAM. I can lay that out. Just 6 transistors, not really difficult. So definitely there are many other ones. You can, it's not difficult as well, but just look at the 6, because you are going to repeat this structure a lot. You know, this is just 1 bit, right? There might be like a gigabits, so you have to repeat it. So you really want to make this one compact. So how? Think about the stick diagram. Layout of the 6 transistor SRAM cell. Think about it. It's 2 inverters, right? And we know how to lay out inverters. Do we? Just 2 transistors. We got 2 transistors, 2 PMOS, 2 NMOSes, and they share the same VDD, and here are the drains. So the same thing for the other one. And here's the ground line. So these are the 2 gates are being shorted together. So that's two inverters. And how to make it into a latch. So now this is nothing but just this. And the gates are shorted together. So gates are shorted together, but the drains are not. So the gates, I don't think I should short the gates together, should I? Oh, yes, I should, because these gates are within the same inverter, so they should be shorted together, right? So this will be the input for the first one, output for the first one, input for the second one, output for the second one. So definitely it should be shorted to here, and this one should be shorted to here. And this is done. Right, and also we need this to form the 6 transistor SRAM cell. And these are two NMOSes, so these two NMOSes should be drawn here in this area. And so if I let the drain of this NMOS share with the drain of this NMOS, will that work? I think so, because the output is being directly shorted to the drain. Right? So these are the two NMOSes here. So what are the two gates of these two NMOSes? The word line. What about the source? Yeah, the bit lines. Done. You just want to make it as compact as possible, since you are going to repeat this for millions of times, right? Okay, decoder. Pretty simple. Just want to double check, see if you guys still remember how to design the decoder. Row circuitry. It's just actually decoders. So here's the logic, A1, A0. For example, I'm just trying to do a 2 to 4 decoder. These are the word lines. And I just want to fire one word line at each time. So for example, this code is going to fire this one, and this one is going to fire this one. It's going to fire this one. It's going to fire this one. So for all the rest of them are zeros. It's a super simple logic. We don't even need a K-map. Just directly draw it like this: A1, A0. So for word 0, you need a A0, A1 not, A0 not. So this will give you word 0 will be activated, and then A not, A0, A1 not, A0. And this is word 1. And then A1, A0 not. A1, A0. Okay, that's a decoder. Boring. Is that boring? In real circuit, so I'm going to show you how to make a clocked decoder. A practical design, let's just call it this. Yeah, you cannot directly just use a combination logic in the sequential circuits. You have to clock it so you can control it, right? So how to do that? You have a decoder here, and these are the NAND gates. There will be many because they are just part of the AND gate. The AND gate, you can enable the AND gate by giving a rising edge. And there will be many of these ones. It's missing one NMOS. The reason is we want to clock the bottom NMOS to control it. So these are shorted together, and these are being shorted to all the word lines in the decoder. -1. What about the other pin? It should be controlled by clock, which is eventually, after you have all the cells together, you just have a final NMOS at the bottom. And you'll short all these PMOSes to this one, and then to this NMOS. And this will be shorted to this line. And these are being connected together as well. Okay, if you do not give a rising edge, nothing will be enabled. Is that correct? Think about it. There's no difference between this one and a regular NAND gate. But all these NAND gates are sharing the one NMOS. And so whenever you open up this one, you can enable this logic because the word lines are being shorted to another pin. Since all the enable functions need to have an AND gate involved, so NAND gate is just has an inverted result. So eventually we still have to invert it. Wait, do we need to short all these ones together? Not to the drain, sorry. The source. Not here. The drains are independent for each cell. Right? Is that making sense? So this one is independent, but only the sources are being shorted to this clocked NMOS. So whenever this is on, for example, this is on, and let's just look at this one. It's just repeating. It's the same for the other ones. If I just look at the bottom one, and if you, for example, you invert it, here's the drain, that's the output. This will be connected to other inverter as well. So that's the final output. So here's a AND gate. That's an AND gate. You just have a clocked signal, and here's a word line. And this will be the actual word line, used in an SRAM cell. And the reason we need this is the decoder and the SRAM cell in between these two components. I have a clocked circuit to enable it. So that's the word line. Whenever this is at the rising edge, it's going to send that word line data to here. So I can use a clocked signal to control the word line being shorted to the SRAM. A NAND gate being inverted, you got AND gate, right? And how to control the clock? You just connect another one, connect the clock signal to the other input of the AND gate. So definitely here you need another inverter. You need the many inverters in between. And all the drains should be shorted together. The sources should be shorted to the drains. Something wrong with it. I shouldn't short this to the drains. So the drains should be controlled by, yeah, there. Sorry for the mistake. All these inverters should be independent inverters, but just the drains. The drains should be controlled by another one. Sometimes they need a sleep signal. So this controls this one, and also this also controls all the other sources of the PMOSes as well. So in that case, when you don't want to do anything with word lines, you can put the entire circuit into sleep. So the way to do that is just directly do what? Give sleep a what? A high, right? Voltage high. Why is that? So whenever this is high, the PMOS is off. So we don't have the pathway to VDD. So all the inverters will not work for VDD for the purpose of pulling this word line to the VDD. So you'll never get a 1 for the word lines. Any word line here. So none of the SRAM cells will be enabled. You just have an extra control here. The clock, it's not really easy to turn the clock sometimes. The clock is always running. You just want to put this in sleep, just give a voltage high here. It's going to turn over the inverters and disable all the word lines. Okay. Any questions? So this is a clocked. Whatever here is just a clocked AND gate. Right? So that's everything about SRAM. So next, I think I'm going to show you what a ROM is. Read only. So the ROM is the first VLSI circuit I have drawn in electrical VLSI 10 years ago. It's pretty simple. So we need a decoder. And VDD here, and all the PMOSes. And they are always on because the gates are grounded. And these are all the lines. They are pre-fabricated in the chip. and this is non-volatile. The reason is you cannot program it. After the company already fabricated this chip, it's already written in there. So for example, I have a decoder here, and that's an NMOS, and here's another NMOS, another NMOS, and this word line is going to turn on all these NMOSes at once, and these are the outputs. For example, it's called Y4, Y3, Y2, Y1, Y0. So read only, so you cannot write it. And this data has been fabricated into the chip at the very beginning, so you can only read it. So if I fire this word line, for example, that's word line 0, and then I'm going to read this data as an output. So what is that output combination? It's still competing, right? We just want to make the NMOS stronger. Because if you do not make the NMOS stronger, it's not making sense to have an NMOS here. Since whenever we have an NMOS here, we just want to pull this data line to 0. Because at the very beginning, all these PMOSes are being turned on. It's a ground. So they're always on. I just want to make this PMOSes weak, but make all these NMOSes strong. So whenever the word line is on, this line will be put down to the ground, and also this one, but not these two ones. So what's the data output here? 0, 1, 0, 1, 0. Okay. So in the old days, it's pretty hard, it's difficult to accommodate every single customer when you are designing a ROM. So normally they will have the NMOSes everywhere. So not just these 3 places, but also here, here as well. It's just for every single row. And before they start trying to use it, so they can program use a laser. So under the microscope, they're going to use the laser to burn this wire to program it. Right? It burns it, just damages this NMOS, so it's not being shorted to this line anymore. So you can program a ROM. But ROM is still being used right now for the BIOS, for the motherboard. Because it's not being changed, it's always there. So whenever you start a computer, it's going to load the data from the ROM, and it's not volatile, so it's very stable. So it will always be there as long as you don't burn it. Right? It's always there. It's programmed. Got 3 minutes, but I don't think we can do anything for DRAM. Let's see how much here. I may need at least 1 or 2 lectures. Are you available after the final exam? Probably not. Yeah, we'll see. Hopefully, Monday we'll do a quick final exam review, and then we'll do DRAM and Flash. And probably we can take some time on Wednesday to cover it. All right, we'll see you on Wednesday. No, see you on Monday. And we don't have a lab on Tuesday, right? Since we're done. And Monday, 10 p.m., the lab report will be due on Monday, 10 p.m. Okay.